You're looking at one right now, an LED light bulb, maybe on the ceiling, on your cell phone screen, on your car's dashboard. It seems so simple, so harmless. A small, efficient light source that replaced the old, hot, incandescent bulbs. But what if I told you that each LED is actually a portal to the quantum world? What if I told you that every time you turn on the light, you're witnessing one of nature's strangest and most wonderful phenomena, a ballet of subatomic particles that can only be described by the laws of quantum mechanics? I'm not using a metaphor. The brightness of an LED doesn't come from a hot filament, like in a fire or an Edison bulb. It comes from countless electrons making forbidden jumps, and, in their fall, emitting a cry of pure light. Each photon that reaches your eyes was created by an individual quantum event. The specific color of that light, whether white, red, blue, is not an accident. It is the exact signature of the energy released in that quantum leap. Therefore, this tiny lamp is not just an object. It is a miniature particle accelerator, a photon factory, and living proof that the universe, at its most fundamental scale, operates in ways that defy our intuition and common sense. Consider the transition we've experienced in recent decades. We grew up with Thomas Edison's light bulbs, those glass spheres with a tungsten filament that glowed intensely, heating up more than illuminating. They were, in essence, small heaters that luckily also produced light. They burned out frequently, consumed tremendous energy, and seemed to belong to an era of brute force. Then, almost overnight, everything changed. LEDs emerged, small, durable, cool to the touch, and incredibly efficient. They produce light in pure, vibrant colors, from intense red to deep blue, something that old light bulbs could only achieve with colored glass filters. How was this revolution possible? How did we go from heating a metal to incandescence to such an elegant and controlled method of generating light? The answer lies not in mechanical engineering or traditional chemistry. The answer lies in a field of physics that many consider abstract and distant, quantum mechanics. The mystery of the efficiency and pure color of the LED cannot be explained by classical physics. To understand it, we need to venture into a realm where particles can be in multiple places at once and where energy comes in discrete packets, like coins instead of a continuous flow of money. My life has been dedicated to unraveling these mysteries and, more importantly, sharing them. I have always believed that the beauty of nature is accessible to everyone, provided we have the curiosity to look and the courage to ask questions. Quantum mechanics may seem intimidating with its complex mathematics and bizarre concepts, but the central idea behind it can be understood through analogies and imagination. And there is no better example to start with than the LED light bulb. Let's take a journey together from the concept of an electron to the glow that illuminates your room. Don't get bogged down in the names or equations. Focus on the idea, on the image we will build. I want you to feel the physics, to see it in action. Let's disassemble the LED, not with a screwdriver, but with the power of thought. Let's look inside its silicon heart and witness the quantum leap that changed the world. I promise you that, by the end of this conversation, you will not only understand how an LED works, but you will also have a glimpse into the very soul of matter and light, a glimpse that will forever transform your perception of reality. To begin our journey, we need to understand the material from which the heart of an LED is made: a semiconductor. Forget the name for a moment and imagine a ladder, but not an ordinary ladder. It's a magical ladder where most of the steps are available for you to step on, but there's a large empty space in the middle, a forbidden step where you simply cannot place your foot. You can be on the lower steps, which we'll call the valence band, or you can be on the upper steps, the conduction band. To move from the lower steps to the upper ones, you need to make a large, energetic leap to overcome the empty space, the forbidden step. This space is what physicists call the band gap, or energy gap. In conductive materials, like copper, there is no such space. The bands overlap, and electrons, the people on our ladder, can move freely. In insulating materials like rubber, this space is gigantic, and it's almost impossible to make the leap. Semiconductors like silicon are the perfect middle ground. Space exists, but it's not insurmountable. With a little push of energy, An electron can indeed jump from the valence band to the conduction band. It is this property, the existence of a controllable energy jump, that makes semiconductors the building blocks of all modern electronics. Now let's populate our ladder. The lower rungs, the valence band, are almost completely full of electrons. Imagine a parking lot with almost all the spaces occupied. It's difficult for the cars, electrons, to move because they are all trapped. On the upper rungs, the conduction band, there are almost no cars. It's an empty parking lot where cars could move freely, conducting electricity. The trick of semiconductors is that when an electron from the valence band gains enough energy, for example, from a voltage, to make the quantum leap and reach the conduction band, it leaves behind an empty space in the valence band. This empty space behaves like a positively charged particle, and we call it a hole. It's as if, in the crowded parking lot, a car leaves, and the empty space becomes a place where other cars can move. So, now, we have a free electron up there, in the conduction band, capable of moving and conducting electricity, and we have a mobile hole down there, which also contributes to conduction. This electron-hole pair is the protagonist of our story. The magic of the LED happens when this electron, after its journey in the conduction band, finds a hole and falls back into the valence band to fill it. This idea didn't come out of nowhere. It was a long and arduous scientific journey. The first LEDs were created in the 1960s and emitted low-intensity infrared or red light. They were more laboratory curiosities than practical lighting sources. Green LEDs came later, but the true holy grail was the blue LED. Why? Because with the three primary colors of additive light, red, green, and blue, you can create any other color, including white, which is essential for general lighting. For decades, scientists tried and failed. The problem was finding a semiconductor material with the exact size of the band gap to produce a photon of blue light, which is very energetic. Many said it was impossible. But in the early 1990s, three Japanese researchers, Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura, after years of tireless work and against the current of thought of the time, achieved the impossible. They developed a method for creating high-quality gallium nitride crystals, the perfect material for blue LEDs. It was such a revolutionary discovery, opening the doors to solid-state lighting and the LED displays we use today, that they were deservedly awarded the Nobel Prize in Physics in 2014. The light that illuminates our world today was born from the persistence and genius of these three men. To make the LED work, scientists don't use a pure piece of silicon or gallium nitride. They use a technique called doping, which is like adding a pinch of a secret ingredient to change the material's properties. In one part of the semiconductor, they add impurities that provide extra electrons, creating an N-type, negative material, as it has an excess of negative charges. In our parking lot analogy, it's like squeezing some extra cars into the already crowded parking lot, eager to go upstairs. In another part of the semiconductor, they add impurities that create extra holes, that is, remove electrons, creating a P-type, positive material, as it has an excess of positive charges. It's like reserving some extra spaces in the crowded parking lot. Then, they join these two parts, the N-type and P-type materials. The boundary where they meet is the most important part of the device, the p-n junction. It is at this boundary that all the quantum action will take place. By applying a voltage in the correct way, positive on the p side, negative on the n side, you force the electrons on the n side and the holes on the p side to move towards the junction, where they will meet and the magic will happen. The p-n junction is the stage for our quantum drama. When you apply voltage, you're essentially pushing electrons from the n-side conduction band and holes from the p-side valence band toward the center. The electrons, energized by the voltage, reach the boundary and look across towards the p side, where they see all those inviting holes, those lower energy states. It's like being at the top of a slide and seeing the pool below. Nature is lazy. It always seeks the lowest energy state. So what does the electron do? It falls. It jumps from the high-energy conduction band directly into a hole in the low-energy valence band. This process is called recombination. The electron and the hole annihilate each other and cease to exist as free particles. But the energy can't simply disappear. That would be a violation of one of the most sacred laws of physics, the conservation of energy. The excess energy that the electron possessed, the energy corresponding exactly to the size of the band gap, needs to go somewhere. And in an LED, this energy is released in the form of a single particle of light, a photon. Billions of these recombinations happen every second, creating the continuous flow of light that we perceive. Let's delve deeper into this moment of the fall. The band gap, the forbidden step on our ladder, is not just empty space. It's a precise measure of energy. It's the minimum energy required to knock an electron from its comfortable position in the valence band and throw it into the conduction band. Consequently, it's also the exact amount of energy released when the electron falls back down. Now, here comes the second piece of the quantum puzzle, an idea from Max Planck and Albert Einstein. They discovered that the energy of light is not continuous, but comes in packets, or quanta, which we call photons. And the energy of a single photon is directly related to its color, or more precisely, its frequency. A photon of red light has little energy. A photon of blue light has a lot of energy. The color of the light emitted by an LED, therefore, is directly determined by the size of its band gap. If the material has a small band gap, the electron's fall will be small, and it will release a low-energy photon, such as an infrared or red photon. If the material has a large band gap, the fall will be greater, releasing a high-energy photon, such as a blue or ultraviolet photon. Color is not a filter. It is the essence of the quantum event. There's a beautiful and incredibly simple equation that governs all of this. It's the equation that connects the world of energy with the world of light, E (half). E is the energy of the released photon, which is exactly the energy of the semiconductor's band gap. F is the frequency of the light, which is what our eyes perceive as color. And H is the famous Planck constant, a tiny but fundamental number that acts as the exchange rate between energy and frequency in the quantum universe. What this equation tells us is that the color of an LED's light is a direct and non-negotiable result of the material it's made of. Engineers don't choose the color. They design the material to have a specific band gap that corresponds to the color they want. To make a red LED, they use a recipe of semiconductors like gallium arsenide that results in a small E. To make the blue LED that won the Nobel Prize, scientists needed to create a completely new recipe, gallium nitride, that resulted in a much larger E. So, when you look at a traffic light with its red, yellow, and green lights, you're not seeing colored filters. You're seeing 3 different types of LEDs made of 3 different materials, each with its own unique band gap, each performing a quantum leap of a different height. Let's try a thought experiment. Imagine yourself as an electron on the end side of the junction. You're in the conduction band, on the top floor of the parking garage, full of energy and buzzing around. Suddenly, an external force, the battery voltage, pushes you toward a mysterious boundary. On the other side, you see the P side, the bottom floor, full of inviting empty spaces, the holes. To get there, you need to take a leap, a fall. There's no ramp, no smooth path. It's a quantum abyss. You take a deep breath and jump. The instant you land in a hole, in the lowest energy state, all the extra energy you had, the potential energy of the height of your jump, is released in a single flash, a scream of light. A photon is born and shoots away at the speed of light. Now, imagine billions of other electrons doing exactly the same thing around you, every microsecond. The result is a chorus of light cries, a symphony of photons, which together form the constant and stable glow we call LED light. It's an incredibly straightforward process, converting electrical energy into light with astonishing efficiency, as almost no energy is lost as heat in this quantum fall-off process. Herein lies one of the most counterintuitive and beautiful aspects of LEDs. They produce cool light. An incandescent bulb works by heat. You heat a metal filament to over 2,000 degrees Celsius until it glows, a process called blackbody radiation. Most of the energy, over 90%, is wasted as heat, infrared radiation, and only a small fraction becomes visible light. This is why old light bulbs are so hot to the touch. An LED, on the other hand, does not rely on temperature to generate light. The electron-hole recombination process is a purely quantum, not thermal phenomenon. The electron's energy is converted directly into a photon with minimal heat waste. This is why LEDs are so efficient and remain relatively cool. They are not shining in the classical sense of the word. They are emitting light through discrete electronic transitions. It's a fundamentally different and more elegant way of interacting with matter to create light. It's the difference between creating music by randomly banging pots and pans, heat, and playing a precise note on a violin, quantum leap. It's the precision and control of the quantum world surpassing the brute force of the classical world. Of course, as with all physics, there are rules and limitations. One of them is the trigger voltage. Since the electron needs a minimum amount of energy to overcome the band gap, the LED will not light up unless you supply a minimum voltage. This voltage is directly related to the energy of the band gap, and therefore to the color. A red LED with its small band gap may need only 1.8 volts to light up. A blue LED with its large band gap may need more than 3 volts. If you supply less than that, nothing happens. No electron has enough energy to make the jump, so there is no recombination and no light. It is a direct manifestation of the quantum, packaged nature of energy. Another limitation, which was the challenge of the blue LED, is the difficulty of creating perfect semiconductor crystals. Any defect in the crystal can create shortcuts or traps for the electrons, allowing them to lose their energy as heat instead of light.
The Nobel laureate's great achievement was precisely in developing a way to cultivate nearly perfect gallium nitride crystals, ensuring that most recombinations resulted in a beautiful and efficient blue photon. The most incredible thing is that this same physical principle that illuminates your room is what powers our entire digital civilization. The same physics of semiconductors, of p-n junctions, of electrons and holes, is the basis of transistors.
And what is a transistor? It is essentially a gate or switch that can control the flow of electrons. By combining millions or billions of these tiny switches on a silicon chip, we create microprocessors, the minds that govern our computers, smartphones, and all smart devices. Each 0 and 1 of the binary code that makes up our software, photos, and music is represented by the on or off state of a transistor. Furthermore, if we reverse the process of an LED, we have a solar panel. Instead of supplying electricity to create light, we use light, photons from the sun, to supply energy to electrons, make them jump the band gap, and thus generate an electric current. Therefore, the LED, the transistor, and the solar cell are 3 manifestations of the same fundamental quantum dance between electrons, holes, and photons in a semiconductor. They are 3 sides of the same quantum coin that defines 21st century technology. And this idea takes us to a truly cosmic scale. The same principle that tells us the color of an LED allows us to decipher the composition of stars and galaxies billions of light years away. When the light from a star passes through its gaseous atmosphere, the atoms in that gas absorb photons with very specific energies, corresponding to the quantum leaps of their own electrons. When we look at the light spectrum of that star, we see dark lines, like a barcode, exactly at the frequencies that were absorbed. Each chemical element, hydrogen, helium, oxygen, has its own unique signature, its own absorption barcode. By analyzing this barcode, astronomers can accurately determine what the star is made of, its temperature, and even its speed, without ever having left Earth. Spectroscopy, as this technique is called, is one of the most powerful tools in astronomy, and it works based on the same fundamental quantum physics that dictates the color of the tiny indicator light on your Wi-Fi. The fall of an electron in a gallium nitride chip in your home and the jump of an electron in a hydrogen atom in a distant star are governed by exactly the same universal rules. This forces us to confront the philosophical implications of quantum mechanics. The universe at its most fundamental scale is not a predictable clockwork mechanism, as Newton imagined. It is a place of probabilities, dualities, and inherent strangeness. The electron and the photon are not simply particles or waves. They are both at the same time, depending on how you observe them. The very act of measuring the system affects the outcome. The location of an electron before it falls is not a defined point, but a cloud of probability. It doesn't be in one place. It has a chance of being in multiple places. The quantum world teaches us that reality is more subtle and mysterious than our everyday experience suggests. It tells us that the universe is not deterministic, but probabilistic at its core. The light from your LED, formed by billions of independent and random quantum events that together create an appearance of constancy, is a reminder of this profound truth. It's a window into a layer of reality where the rules of our macroscopic world simply don't apply. A reminder that nature has far more imagination than we do. And what comes next? The solid-state lighting revolution is just beginning. Scientists are already developing the next generation of lighting and display technology. We have OLEDs, organic light-emitting diodes, which use organic molecules instead of semiconductor crystals, allowing the creation of ultra-thin, flexible, and even transparent screens. Imagine one day rolling up your TV like a newspaper. We have quantum dots, which are semiconductor nanocrystals so small that their band gaps can be precisely adjusted simply by altering their size. This allows for the creation of incredibly pure and vibrant colors, as seen in QLED TVs. And there are even more exotic technologies under development, such as Li-Fi, which uses the rapid oscillation of LEDs, too fast for our eyes to perceive, to transmit data, potentially offering internet speeds far greater than Wi-Fi. The same device that gives us light could give us connectivity. Our mastery of the quantum leap continues to evolve, promising a brighter, more efficient, and more colorful future than we could have imagined. Despite our incredible ability to manipulate the quantum world to build LEDs and computers, fundamental mysteries remain. What is a photon really? Is it a particle, a wave, an excitation of a quantum field? How does gravity, which governs the cosmos on a large scale, fit with quantum mechanics, which governs the subatomic world? This is the biggest unsolved question in modern physics. We have two incredibly successful theories that describe the universe, but they seem incompatible. Light, which is a quantum phenomenon, has its trajectory bent by gravity, so the two must communicate somehow. But we still don't know the language they use. What happens to information when an electron and a hole recombine? What is the quantum measure that forces a particle to choose a state? These questions take us to the frontier of human knowledge, where science meets philosophy. The humble LED light bulb at its core is not just a piece of technology, but a constant reminder of those profound and beautiful mysteries that we are still trying to unravel. Let's recap our journey to the heart of the LED. First, we discovered that it's made of a special material called a semiconductor, which has an energetic, forbidden step called a band gap. It's the existence of this step that makes all the magic possible. Second, we saw that by applying a voltage, we force electrons to jump to a higher energy level, and then they fall to fill empty spaces called holes. This process is electron-hole recombination. And third, the crucial point. When the electron falls, it needs to release its extra energy, and it does so by emitting a single particle of light, a photon. The energy of this fall, determined by the size of the band gap, defines the exact color of the light. From low-energy red to high-energy blue, the color is the signature of the quantum leap. In a remarkably elegant way, the LED converts electricity directly into light with an efficiency that classical physics could never dream of achieving. What can you take away from this for your daily life? Beyond a newfound appreciation for the little blinking light on your router, the practical lesson is about efficiency and the beauty of ingenuity. Every time you choose an LED bulb instead of an incandescent one, you're making a choice based on fundamental quantum physics. You're opting for a device that wastes far less energy in the form of heat, which translates to a lower electricity bill for you and a smaller environmental impact on the planet. It's one of the rare cases where the most technologically advanced solution is also the most economical and environmentally friendly. Quantum mechanics isn't just a strange theory on a blackboard. It has real and beneficial consequences in our lives. It allows us to do more with less. It illuminates our homes, powers our devices, and in doing so, helps us conserve our world's precious resources. So, appreciate this little marvel of human ingenuity and fundamental physics. I want to conclude with what I consider the most important idea of all. Science is an adventure of the imagination. It's the ability to look at something common, something everyone sees, and perceive the invisible structure that sustains it. It's looking at a simple light bulb and seeing a ballet of electrons and photons, a dance governed by quantum laws. Don't be content with the surface of things. Always ask yourself, how does this really work? The joy of understanding, of connecting the dots between an everyday phenomenon and a profound principle of nature, is one of the most rewarding human experiences. The universe isn't trying to hide its secrets from us. It's openly displaying them everywhere, in every beam of light, in every drop of water. The only tool you need to unravel them is your own curious mind. Keep using it. Keep asking questions. Reality is much richer and more fascinating than it seems, and the act of understanding it is what makes us truly human. Don't miss the chance to participate in this incredible journey of discovery. Now that we've unlocked the quantum secret of the LED, which transformed how we see light, what other everyday mystery would you like to explore? Physics is behind everything, from how ice floats, an accident that made life on Earth possible, to the workings of the liquid crystal display on your cell phone, which uses an impossible state of matter. Which of these ideas sparks your curiosity the most? Leave your opinion in the comments. What object would you like us to take apart next, using only the power of thought? Your curiosity will guide our next adventure. And the next time you turn off the light, remember, you're not just pressing a switch, you're ending a symphony of billions of quantum leaps.